Hello everyone, my name is Tianyi GU. Today I'm going to present our paper on real-time planning as decision-driven decision-making, data-driven decision-making. And this is a joint work with Max Vickert, Leo Start, and Siley Qiang, Professor Wheeler Ruml, Professor Jörg Hofmann, and Professor Mark Patrick. We are from Saarland University from Germany and the University of New Hampshire from United States. So for the problem settings, we are dealing with a single agent, discrete state, discrete action, and we have a fully observable states. We are doing online planning, meaning we interleaving planning and action execution. We have a deterministic state transition, meaning we don't have any stochasticity on actions, all right? So for the real-time heuristic search, we can't wait until we have a full plan to do the execution. So we have to return the next action within a given time bound. Here's an example of a path finding domain, and we have an agent, have a goal state. We want to find a path that drive the agent from the initial state to the goal state without collide with any obstacles. So for real-time search, what we do is we perform a search up until the time bound. And then we find the best node among all the search frontier, and then we commit the best top level action which will drive the agent towards to that best frontier node. We commit that action and then the agent will execute that action, and then we perform another round of search until the time bound. We doing this interleaving search and execution again until the agent reach the goal. This is also called a receding horizon control. So the challenge here really comes from the time bound, meaning we would have a limited time to perform search. So we can only do limited look ahead, which leading to value uncertainty of the actions. And then in this work, we begin to trying to find a rational approach for real-time planning. We borrow ideas from Bayesian RL, and we work in a simplified settings compared to conventional RL settings so that we can put focus on bounded rationality. All right, in our previous work, we proposed this new real-time framework called Nancy, which trying to address several problems of the conventional approach. Here is an example of a troublesome example for the look-ahead strategy. For example, if we have two top-level action, right now, the alpha and the beta. And if we can have the expected value to represent the value of the action, so this we're using the f hat, the estimate the cost of that action towards to go. So then if here we know that the expected value for alpha is actually lower than the expected value of beta, does that mean we want to do more search under alpha rather than beta? Right, because just in looking at this scalar value, we know that the subtree and the alpha looks more promising. It can leading us to lower cost solution. Well, it's not quite obvious. So for example, if we can somehow form the uncertainty as a belief distribution of that value estimate and the alpha, and then also in the beta. And then if in this case that the agent is quite certain about the value and the alpha, and then quite uncertain about the value and the beta. So in this case, it might be more helpful to do more look ahead, to do more search and the beta, so that in the end of the search, the agent have and can have more confident about which action to commit, right? So if a scalar hat value, a single expected value is not the answer, what to do, right? So here, what we really want to maximize is maximize the value of information. We really need to consider the uncertainty of the estimates. So in our approach, we propose to expand the nodes which minimize the expected regret, which we accumulate all the regrets that in those cases where alpha is not the best action. All right. So really, we want to solve the question of how to best use this limited number of expansions. You know, if we expand during the search, we can have a huge search tree, and then we can form our belief distribution about our value uncertainties everywhere in the search frontiers. And then how to use those informations to guide our search to give us better solutions. It's not quite obvious, right? So in our approach, we have a couple things to do. First is we have to estimate the value uncertainty. So one option would be to using, you know, kind of distance to go, which is correlated with uncertainty, using that to do the estimation. And then once we have the estimation, we have to use the estimate to guide the search, right? For those details, please see our AAAI 19 paper. And then we can also use data to estimate those distribution. For detail, please see our AAAI 20 paper. In this paper, we do more experiment. We compare our Nancy approach against the other methods that also try to exploit value uncertainty. We also have a visualization of the distributions. For example, here are some results. And what does the actual data look like, right? So here we're showing an example of a classical planning domain, a transport domain, and a blocks world domain. So for all the H values, we collect the data. We collect those states have that particular H value. For example, for H value equals 6, we collect all those states and then compute their optimal cost to go, H star value, and then plot it here along the y-axis. As we can see, the distribution of the optimal H star value is actually looks very different from domain to domain. Some of them could be unimodal, some of them could be multimodal distributions. So we can visualize those distributions of value uncertainty. And then given those distributions, we can plug it into our search to use it to guide the search. And so here's an example of the result search algorithm. We compare the algorithm against the conventional ARSSRT star approach. Also, we compare Nancy against other methods that also take into account value uncertainty. For example, THTS is a variation of a Monte Carlo tree search, which using to adapt to deterministic domain. Also, interval estimation is another approach, as we can see here. And so the cost is lower, the lower the better. As we can see, Nancy performs good in this domain. We also have the results in other domains, for other domains in our paper. All right, to conclude, Nancy starts to explore an optimal way of doing online heuristic search. It is competitive or even better than conventional approaches. More broadly, for the deterministic domain settings here, we really isolate the issue. Unlike conventional MDP or RL approach settings, here all the uncertainty is only due to bounded rationality. And meta reasoning about this uncertainty really pays off.